Right. Before we get started, in addition to the regular place where Bill and Roger put all of our studio webinars, I've also put the slides and the code for today at this bit.ly link. And just like last time, the bit.ly link will persist at the top of the slide deck. So you'll see it throughout the webinar today. You don't need to write it down right away. But if you want to follow along with the code and the slides, you can visit there and download the materials. It's about 5 megabytes. And then just like last time as well, I'm going to be looking at some really simple examples of Shiny to make things easier for learning. There will be no bells and whistles and no distractions in these examples. And I don't want anyone to get the impression that Shiny only makes really simple apps. If you would like to see Shiny apps used to their full extent, or the way people, at least in the business world, use them, please visit the Shiny Showcase, where I've collected many examples that show off more of the capabilities of Shiny beyond what we'll learn today. So this is the second of a 3-part webinar series. The first part was an introduction to how to build Shiny apps, and it's now available at this web address. And so if you missed that webinar, you could check it out and watch it for free there. Today we're going to look at how to customize reactions in your Shiny apps. And then a week from today, we'll look at how to customize the appearance of your apps. So if you notice that our apps look kind of plain and we haven't done much with the layout or the visual appearance of the apps, don't worry, that will be the topic of the last webinar. So let's review where we left off last week. During that webinar, we learned the basic architecture of a Shiny app. Every Shiny app is a web page that contains R components. And attached to every Shiny app is some computer, normally a web server, that is running with an open session of R. And when a user changes an input on the web page, for example, selecting something from a drop-down menu, then that server running R immediately responds by generating some new R output to place in the web page. For example, they might generate an up-to-date graph or an up-to-date table. And so this idea of a web page and a computer running R is fundamental to the idea of a Shiny app. We looked at a template for building Shiny apps in the last webinar that involved 4 lines of code. And the template revolves around building a UI object, which lays out the web page for the app. This object will eventually be written in HTML, but you create it with R functions using R code, so you don't need to know HTML to make a UI. And then you write a function for the server to use to create the R components for the app. This is where we'll spend our time today. We'll focus on writing the server function. And then finally, the template knits together the UI and the server components of the app to create a full-fledged Shiny app. We used that template to look at the basic components of an app. We learned how to add inputs to your app with input functions provided by Shiny. For example, this function adds a slider to an app. We looked at how to add space for output objects. These are the display objects you build with R but show to the user in your web page, with the output functions, which also go into the fluid page function that's saved into the UI object. We learned that even though you've provided space for an output object, you still need to build the output in the server function using the computer that's running R, and that you do this in a 3-step process. Every output you want to add to the app, you have to save in the server function as output $, a name, and that'd be the same name you looked up the output with in the UI file. Second, you build the output to display with a render function. For example, render plot would render a plot, but there are other render functions that render other types of things. And third, in the code you use to actually build the output, if you use an input value, which you can access as input $, in the name, Shiny will take care of reactivity for you. So if you make an output that uses an input value, then whenever that input value changes, so long as you follow these basic rules, the output object will change as well. It will be connected to the input object and it'll stay up to date. During the course of that webinar, we made this app, and I'll use it as an example app for some of the examples today. It's just a simple app with a slider and a histogram that changes when you change the slider. And then we ended that day by looking at how you could share your apps. Shiny web apps are web documents, so they're made to be easy to share over the internet should you choose, or some other HTML-based intranet. You could share all of your apps for free on a server hosted by RStudio called shinyapps.io. And I explained that to get started with shinyapps.io, you could just visit that website, shinyapps.io. And I also explained how you could build your own server using either the open source Shiny server product or the professional version of Shiny server. And both of these just build a Linux server that you are in control of and you own to host your Shiny apps on the internet. If you don't believe we went over all these things, or you didn't attend the last webinar, you can find it here at this link and check up on all these facts. And I encourage you to do so. Going on for the rest of the day, I'll assume that you have a basic acquaintance of the material we covered in the last webinar. So let's start with reactivity. I think the easiest way to think about reactivity or get an intuition for reactivity with Shiny apps is to think about Microsoft Excel, because Excel is probably the most common place where we find reactivity in our day-to-day lives. If you open an Excel table, a spreadsheet, you could type some value into a cell, and then you could go to a new cell and type in a formula that uses the old cell. So this is a formula that takes the fourth row of the F column where I typed 50 and adds 1 to it. Once I hit enter, it computes that formula. And now whenever I change the cell in the F column, the cell in the J column will react. It will automatically update, so it's always equal to the F cell plus 1. This is reactivity, and this is also what Shiny does. The effect of this is that it seems like changes in the F cell are propagated over to the J cell. In Shiny, we do something similar, but instead of working with cells, we have input objects and we have output objects. And changes in our input objects get propagated to the output objects, as if there were 2 cells in a spreadsheet. Of course, there are no spreadsheets involved. Instead, our input objects are things like sliders and action buttons and drop-down menus, web elements that your user can manipulate. And our output objects are things to display like tables, graphs, visualizations, that sort of thing. Now, in Shiny, reactivity is much more sophisticated than just inputs and outputs. We could also do things like this. We could use a change in an input object to trigger some arbitrary code to run on the server side, or we could extend our chains of reactions. So we could have changes in inputs create secondary objects that are themselves reactive, and changes in those objects can trigger changes in our outputs. We could control our reactions. For example, we could insert something like an update button into our app, so a change in an input will eventually change an output, but not until the user asks it to by clicking the update button. And these sorts of things are going to provide the material that we go over today. We'll go look at how to start with inputs and create all these different patterns of reaction within your Shiny app. We'll go begin with reactive values, because that's where reactivity starts with Shiny. So we know now that you can create an input object with an input function, and you could give that input function a name with the input ID argument. Once you do that, the value of the input function will be available to use in your code in the server function. So for example, this input function here creates a slider, and every time the user changes the slider, the value of that slider input, named input $num, will change as well. So the value will always show the up-to-date value of the slider object. This is what a reactive value is. It's a value that changes, reacts to some sort of input. And it's different than other R values because it can change at a moment's notice. Most values in R only change when there's a piece of code that actually tells them to change. And normally you're the person who writes that piece of code. These are a little different. Reactive values in Shiny don't work on their own. They actually work together in relationship with a function, a reactive function. Reactive function is a term I'm just going to use today, and all it means is a function that expects to take reactive values and knows what to do with them. These two ideas, reactive values and reactive functions, work together to create the reactions we'll see in Shiny. And so if you try to do something with only one of these components, for example, if you try to use a reactive value like input $num, but didn't pair it with a reactive function like render plot, which we were using last time, you'd get an error. In fact, this is a pretty common thing to do in Shiny. Notice in the app that we made last time, the code's over here on the left, we're using a reactive value to create this histogram. And we're using a reactive function, render plot. It's a function that expects to take reactive values and knows what to do with them. And together these things create the app that we see. If we decide not to use render plot, or we forget to use render plot, and just call the reactive value, you'll get this error message. And as a beginning Shiny developer, this will be a very familiar error message, so we should take a look at it. It says, the operation is not allowed. You're doing something and not doing something in an active reactive context. This is technical speech, but all it means for you is that you try to use the reactive value without also using a reactive function to work with it. And if you see this error message, it means you need to think of what reactive function you want to use to do what you're trying to do. Now, I've said that render plot is a reactive function, but we'll see today that there's more functions you could use besides just render plot. So this idea of reactive values working together with reactive functions breaks reactivity in R into a two-step process. Now, here's a visualization of the app that we made last time. You'll see that this app has a reactive value created by the slider. That value is named input $num, just because of the way we wrote the code. And then this app has a reactive function render plot that is using input $num to create an object that's being saved to output $hist. I'm going to call this object created by the reactive function an observer. And together, the observer and the reactive value create the reactivity in the app. When you change the slider, here we'll change it from 27 to 25, it changes the reactive value input $num, and then the reactive value does its job. The job of reactive values in reactivity is to notify things downstream that they've changed. So step one, the reactive value notifies the objects that depend on it that it has changed. And now its job is mostly over. It's time for the reactive function to do its job, or more precisely, for the object created by the reactive function to do its job. And what its job is to just respond in some way. When you have a render function, it creates an object whose job is to rerun the code that you pass to the render function to update itself. So here, once notified, output hist will rerun the code. The code calls input num, so look up the value of input num, and once it has it, it can create the new graph and put it into the plot. So those are the two steps of reactivity. Reactive values notify the things that depend on them that they've changed, and then the things that depend on them respond in some way. The way to customize their response is to use the correct reactive function to do what you want to happen. Which means our job today will be to learn what are the different reactive functions we can use and what are the things that they do. So let's just recap reactive values before we look at all the functions we have at our fingertips. Reactive values act as a sort of data stream that flows through your apps. They're the changes that cause reactions downstream. The input list in your app is a list of reactive values, and these values are designed to always show the current state of the input objects in the Shiny app. You can only call a reactive value from a reactive function, which is a function that's designed to work with the reactive value. And then finally, you could think of reactivity in R as happening in two steps. Reactive values notify the things downstream that they've changed. This is a process called invalidating. So a reactive value notifies an object that has become invalid, and then the object, which has been created by a reactive function, responds in the way that that function programmed it to respond. To completely control reactions in Shiny, there's only about 7 functions you need to learn. I'm going to call these the reactive toolkit. So let's take a look at these functions one at a time. The first one will be familiar. But as we go through the functions, it can help to think of 2 things related to the functions. Almost all of these functions are going to take a chunk of code, and they're going to use that code to build and rebuild some sort of object. And then second, the object created by the reactive function will respond to changes in a set of reactive values. It will be notified by certain values or invalidated by certain values using that vocabulary. If you want to understand these functions at a deep level, then when we go through them, I suggest you ask yourself 2 questions. First, for each function, ask yourself, what code will the function actually use to build the object or rebuild the object? And second, ask yourself, what reactive values will the object created by the function respond to? So it'll normally be obvious what code the function is going to use, but it'll be a little more subtle to understand which reactive values the object will respond to. But of course, that's a very important part of the process, and I'll try to make it clear. The first set of functions in the reactive toolkit are the render functions, which you've already seen in the last webinar. So Shiny comes with a family of functions that each create a certain type of output that you can display in your final Shiny app. The most common of these functions are probably render plot, render table, render text, and they build something that can actually be displayed. To use one of these reactive functions, you just need to give it one argument, and that's a chunk of code or a block of code that the function uses to build the display object and to rebuild the display object whenever it changes. This block of code should begin with the curly brace and end with the curly brace. Between the curly braces, you can put whatever you want. You can even put multiple lines of code. You could put 100 lines of code if you want. The curly braces will unify that code together so it can be passed on as a single block of code to the object that renderplot makes. This object will respond every time a reactive value in the code block changes. So you could have one reactive value in that code block, you could have 10 reactive values, you could have 0 reactive values. But whenever a single value changes, the object created by renderplot will be invalidated, which means it will, in this case, rerun that code to build a new version of itself that is up to date. And this is an important point. When you pass a block of code to renderplot, that block will always be run as a single unit. When it's time for the object, for example, the graph that renderplot makes, to be re-updated, that entire block will be run. Renderplot can't do anything to determine, which parts of the block are out of date and just run those parts. It just always runs the whole block of code each time. So let's take a look at how that works out. In the downloads for today, there's several R scripts. This is the first one. And it just creates a simple app that has 2 input objects, a slider and a text field where you can write a title. And then it uses those to make a histogram. One thing you'll notice is that histogram uses both of the input objects. So it uses 2 input objects to do its job. You could visualize the app like this. Here's our 2 input reactive values. And here's the observer object created by renderplot and saved to output hist. If you were to type a new title into the title field, for example, I'm going to try to change the title to very interesting data, then the reactive value input $title will change, and it will notify everything downstream that depends on it that is changed. This notification invalidates output $hist, and since output $hist was made with a render function, it's going to respond in a certain way. It's going to rerun the block of code in the render function to update itself. When it runs that code, it's going to call input $num, even though input $num hasn't changed. It's just running hist rnorm input $num. It gets that value, and then it gets the main equals input $title, and it gets that value. And once it has both those values, it can make the new plot, which will then appear in our app. So that's pretty straightforward, and that's very close to what we looked at last week. And that's how the render functions work. They make objects to display. Whenever you want to make an object to display in your app, you're going to use a render function. You always save the results of the render function to output $, because that's the only way to get the results into your app. And then the render function makes an object, an observer object, that has a block of code associated with it. That's the code chunk you pass to renderplot. And whenever that object becomes invalidated, it will rerun that entire block of code to update itself. So that's pretty straightforward. Let's look at how we can make things slightly more sophisticated. Here's a similar app. This app has one input, a slider, but it has 2 output objects, a histogram and then a block of text, which includes summary statistics at the bottom. And you'll see over here on the left, I'm making that block of text with the new render function, render print, which renders the output of what gets printed into R. Each of these output objects use the same input object, input $num, which means our app looks something like this. We have one reactive value, 2 things depend on it downstream. When that reactive value changes, for example, when we move the slider, it notifies both of those objects that they're invalidated, and then these objects rerun the code blocks to update themselves. So first, the histogram will rerun its code block. It's going to generate input $num random normal values, and it's going to plot them as a histogram. And then the second observer object, output $stats, will rerun its code. It's going to generate input $num random normal values and print out the summary of those, and that updates that part of the graph. Now, one thing about this arrangement is we're calling rnorm input $num twice, once for each object, which means each object is generating its own data set to describe. The histogram is describing one data set, and then the summary statistics at the bottom are describing a second data set. Now, that's not generally the sort of behavior we'd want in this sort of app. And what we'd like to think about doing is make sure that both output objects describe the same data set, which is something we could do. Our strategy for doing this would be to, instead of calling rnorm input $num twice in this app, call it once and save the data set it creates, and then use that data set downstream where we need it. Now I put a question mark here by the assignment operator because it's not clear yet how we should save the data. First of all, rnorm input $num does contain a reactive value, so we need to use a reactive function to work alongside that value. And second of all, we want this data set to do something specific. It's going to get notified by input $num when it becomes out of date. We want it to pass on that message to things that depend on it, that they too are out of date. So these jobs are what you can do with the function reactive that occurs in Shiny. Reactive builds a reactive object, which is called a reactive expression in the Shiny vocabulary, that takes input objects, assembles them together into some sort of output. Could be a data frame, could be a single value, could be a plot, and makes that output, that result, available to use later on in other code. To use reactive, pass it a code block. Reactive will use this code to build and later on rebuild the object you're making. And then, just like with render, the object will respond to any reactive value in the code block that changes. Reactive expressions sort of emulate R objects. You create them and then you use them again later. But they're actually different in a couple of ways. In the first way, the most important way for avoiding errors, is that reactive expressions are technically functions. And if you want to use it later on in your code, if you want to use the data that we store in data, you'll have to call data as if it were a function. That means you'll have to put an open and close parentheses behind the name data. There's no arguments involved, just open and close parentheses. If you forget the parentheses, then R will do the same thing it does whenever you type in a function name with no parentheses. It'll show you the code inside that function. Now, normally that's not what you're looking for inside your Shiny app. You almost always want to put these parentheses. So if you're getting weird error messages, check and see that your reactive expressions have parentheses behind their names. So if we wanted to use a reactive expression to modularize that app we were looking at, this is how we could go about it. We could take our two instances of rnorm input $num and create a reactive expression that builds the same thing. It calls rnorm input $num. I'm going to save the result of this reactive expression to data, and then down here, for each of the instances of rnorm input $num, I'll replace it with data. So we're building this data set once, and we're accessing it twice. But now, both hist and stats will be accessing the same data set. Let's look at how this works when we start playing with our app. If we were to change the slider now, input $num would notify the reactive expression that it's invalid. And then the reactive expression, what they do is they simply notify the things downstream that they too are invalid. The reactive expression didn't recompute any results or anything, it just passed on the notification. Now we get to the output objects created with the render functions. The job of render functions is to rerun their code when they become out of date. So now output hist is going to rerun its code. It's going to call hist data, which means it's going to call data. When it does, the reactive expression knows it has to return a value. The reactive expression is out of date, it doesn't know the right value to return, so it now runs its code. And when it runs that code, it looks up input $num, gets its value. The reactive expression computes itself, saves its result, passes that result to hist, which can now make the new plot. And now it's output stats time to return to rerun its code. And here's the second thing that reactive expressions do that's different than regular R objects. Reactive expressions know whether they're valid or invalid. At the moment, this reactive expression is valid because it just looked up the new value of input $num, and nothing has changed since then. Reactive expressions also save their result in your computer's memory. So the reactive expression has two options now for returning a result to stats when stats calls it, which it will. Stats runs summary data, calls data. The reactive expression either recompute its code to arrive at the value, or it could take the value that had stored in memory and just give it to stats, since it knows that value is up to date. Reactive expressions will always just return the value they have stored in memory, their cached value, to avoid computation when they're up to date. So why does this happen? You can imagine a reactive expression that takes 50 lines of code to compute its result, and if it's up to date, there's no sense in wasting time recomputing 50 lines of code. It already has the result stored in memory. It doesn't need to arrive at the result twice, so it just passes on that result. If the reactive expression knows it's invalid, then it runs the code. So you could think of the second feature of reactive expression as reactive expressions cache their values. And the expression will always return its most recent value, which is cached in memory, unless the expression has become invalidated, at which point it reruns its code and saves the new value. All right, so let's recap reactive expressions. They make an object to use. These objects don't appear in your app. Your user doesn't see them, but you could use them in code that does make objects to display. You could use reactive expressions to modularize your apps because they're also reactive, so they fit in as a link in the reactive chain. You call a reactive expression like a function with parentheses behind it. And then reactive expressions cache their values, which can save you computation. Well, it'll save your app computation. In practice, you don't even have to worry about them caching their values. That's just a feature Shiny takes care of for you. So we've learned how to make a chain with render, and we learned how to extend a reactive chain with reactive. Now let's look at something a little more simple, isolate. Here's our app we looked at 2 apps ago. It's the one that creates 2 inputs, or uses 2 inputs to create an output. And if we go over to RStudio, we can actually take a look at this app in practice. If you download the files for today, this is what the folder you get looks like. It has the slides for the day and then the code. And inside the code are 8 different apps to look at. And this one's just the first app. So if I highlight all this code and then run it at the command line, and Command Enter, keyboard shortcut to do that, I get the app over here. You'll see that when I change the slider, the histogram updates. And also when I change the name, the histogram updates. Now it could be that I have a good name in mind, but it could be that I'm a slow typer, and so the app is starting to react faster than I am actually reacting. And at the moment, I don't like that. So I'm going to try to circumvent that behavior. What I want to do is find a way to prevent the app from responding to the title field. So the app will still respond when I change the slider, but in the meantime, I'll have the freedom to type in any title I want, and the app will not respond to that. You could do that sort of thing with isolate. So isolate is analogous to reactive, in that reactive creates an output that is still reactive. Isolate creates output that is not reactive. You give it reactive values to assemble into some output, some result, and then it gives you back the result. But the result itself is just a normal R value. Nothing will react to it. It's not a reactive value. The arguments for isolate are similar to the functions we looked at already. It just takes a block of code that it uses to build its result, but then the result will not respond to any reactive value in the code. The result will be inert. So if we wanted to use isolate in this app, and we only want input title to be non-reactive, then what we would do is we'd surround input title where it appears in the app with isolate. So isolate's go to fetch the value of input title, but it's go give back the value in a non-reactive state. In practice, this means that once we put isolate around input title, the observer object won't have a dependency on input title. It'll use input title, but it won't react to it. So now we can change the title, that'll change reactive value, but there's nothing downstream of the reactive value to notify. So things will just stay as they are. If you change the slider, it's not isolated, so the output object will still depend on it. It notifies that object. And then the output object does its job. It reruns all the code there. First thing it looks up in the code is input $num, but then after it has that, it moves on and it looks up isolate input $title. It's going to look up that value just like it'd look up any value, reactive or not. It's going to use it to create a new plot, so the new title will show up in my plot when it's time to make a new plot, but the plot simply will not react when the title changes. So isolate is pretty straightforward. It makes non-reactive objects out of reactive objects. And you could use isolate to treat reactive values as if they're normal R values to sever the chain of reactivity. All right, let's look at the bigger picture and see where we are right now. We're learning of many different ways to create reactivity. It's a bit technical today, I apologize for that. But we've learned several ways already. We've learned to create the basic chain of reactivity from an input to an output object with the render functions. We've learned to extend that chain of reactivity with the reactive expression. And we also learned how to break the chain with an isolate expression. Now we're going to look at how to trigger code on the server side based on changes in the input objects. So this is code that your user probably will never see, but the server will handle. It could be things like writing a new file to save for later, downloading a file for your user to use. We'll talk about some of the ideas. To do this, I'm going to use a new type of input object called an action button. It's in the same family of functions as slider input is, and it doesn't work very differently. It takes an input ID, it maintains a value that we could access in the server side, and it takes a label. In this case, this label would be click me. And what action button does is it inserts a button input object into your app. So we could add it to the basic template, and we'll get an app that looks like this. It has a simple button in it. I could click that button, but at least when the app looks like this, nothing's going to happen because I haven't written anything in the server side of the app. The way I'm going to trigger code based on clicks of that button is with the function called observe event. Observe event is slightly different than the functions we've looked at before because it uses a different syntax. The first argument of observe event is either one reactive value or a vector of reactive values. And these are the values that observe event is going to follow, to track, to get notified by. So observe event will react whenever one of these values changes. It's going to create an object, an observer object, that exists in your memory. You can think of this object abstractly because it doesn't create a display output. No one's going to actually see this object, but it's going to be there and it's going to react to changes in these reactive values and only to changes in those reactive values. That's important because the second argument of observe event is a block of code to run whenever one of those first reactive values changes. This block of code can contain its own reactive values. It can use them, but changes in those reactive values will not trigger the observe event to invalidate unless those reactive values also happen to be in the first argument. So you could think of this block of code as being wrapped in that isolate function we just learned about, which means you could use these reactive values without pairing them up with a second reactive function. R will treat them just like normal R values. And second, just because the values appear here in this code chunk, they won't trigger the observer to update when they change. All right. So here's how I would use that in my app from before. I'm creating an observer with observe event. Notice I don't need to save it to anything. It'll just appear in the memory for this app, and it'll start working. The observer is going to update whenever I click the button because the first argument here is input $clicks, the name of that button. And then when it updates, it's going to run that block of code I gave it. I can give it any code that R can run. So really I could have it trigger anything I want. What it triggers will be run on the server side, so it doesn't automatically appear back in the app. You need a render function for that. But let's take this app and see what happens in RStudio. So this script is called action button. It's the 5th script. Take a look at here. It's just what was on that slide. And if I run it, it's going to create an app that looks like the app in the slide. It's just a click me button. But you'll notice when I click this button, something's going to appear in my R console down in the bottom corner of the screen. I clicked it once, and the number 1 appeared. Clicked it twice, the number 2 appeared. And every time I click it, something else appears in my R console. Now remember, when you run Shiny Apps locally, your R session here is the server for the app. So what I'm doing over here is causing something to happen on the server back here. What's happening is it's just printing the value of input clicks. So here we can see how action buttons work. They maintain a value that begins at 0, and every time you click the button, the value increases by 1. This lets action buttons do their job. The value of an action button isn't meant to be meaningful, it's just meant to create a change that things can respond to. So just out of simplicity, we just have it add 1 each time. That's the change. If you're using action buttons in your apps and you find that your app depends on the specific value of the action button, then there's a chance that you're using the action button inefficiently. In fact, there's a really good chance because your app should never depend on the actual value of the action button. If you want to learn more about action buttons, we've written a whole article on it that you can find here, shiny.rstudio.com. And the article will give you some good advice and best practices for working with action buttons. Along with observe event, which triggers code, there's a second function called observe. It does the same thing. It's a parallel to observe event, but the syntax is more similar to render, reactive, and the isolate functions. With observe, you just give observe a single block of code to run, and then observe will rerun that block of code anytime one of the reactive values in the block of code changes. So the syntax really is similar to render, reactive, and isolate. If you want to use that syntax, then use observe. I found in practice and in teaching people that the precision of the observe event is both easier to think about and tends to be more useful in the long run. But observe is an option. All right. So let's recap what we learned about triggering code. Observe event triggers code that gets run by the server. This is a good way to do things in the background like connect to databases, download data, save data, write to files, do anything else that the server might be interested in. Observe event lets you specify precisely which reactive value should invalidate the observer. Usually you'll put something like a button into your app, and observe event will track that button. So when the button's clicked, it will invalidate the observer. You could use the more implicit general syntax with the function observe, which does the same thing as observe event. It triggers code to run when it is invalidated, but it tracks every reactive value in the code that you give observe. All right. So usually once people get the handle of these things, creating reactive chains, expanding them with reactive expressions, the next thing they want to do is delay reactions. In fact, you might have thought that when we used isolate to prevent the title of our histogram from updating the plot, that was a bit excessive. We could have just delayed the reaction until we were done typing the title. Well, you could do things like that in Shiny. I'll show you how. I'm going to use our basic app from the last webinar as an example. It's a histogram and a slider. And what I want to do is add an action button to this app, which is easy enough to do. And this button says update. And my thought is I would like the slider to not change the graph. I would like the update button to change the graph. So in other words, I'd like to be able to move the slider as much as I like, but not have the graph respawn until I click the update button. The way to do this in Shiny is with the function event reactive. Event reactive makes a reactive expression just like reactive does, but it has a different syntax. The syntax of event reactive is much more similar to observe event. The first argument you give it is either a single reactive value or a vector of reactive values to respond to, and only these values will invalidate this reactive expression. The second argument is code that it will use to build the object and to rebuild the reactive expression object when it's invalidated. But just like with observe event, it'll treat this code as if it has been isolated, so it will not respond to changes in the reactive values in that code unless those values explicitly appear in the first argument. We can use this idea to make our simple app, to delay the reaction in the simple app. In the output, I'm making a histogram that depends on this data set that I'm creating with input num. There's no real reason to use a reactive expression here because the app is so straightforward, but I can use a reactive expression. There's no reason not to. And what I'll do is I'll create a reactive expression with event reactive. This reactive expression will invalidate when the go button is clicked. That's the button that says update up there. And when it's invalidated, what I want it to do is recompute the data set using the code I'm using below, rnorm input $num. And then down below, I will use the reactive expression, instead of rnorm input $num. So now the histogram depends on a reactive expression that only invalidates when someone clicks the button. If we look at how this app works, if we visualize it, see there's now two input objects, the slider and the go button. And there's the reactive expression and the single output. When you change the slider, that reactive value changes, but there's nothing downstream for it to notify. When you click the update button, the input go value changes, and it is associated now with this event reactive, so it notifies event reactive. Event reactive knows it's invalid. It does what every reactive expression does. It tells everything downstream that they too are invalid. Here the notification gets to an observer created with a render function, so that observer is going to rerun its chunk of code to update itself. When it updates itself, it calls the reactive expression. The reactive expression has been called and it knows it's invalid, so it's going to rerun its code. When it does that, it's going to call input $num. So it will retrieve and use the most up-to-date value of input $num. It just won't take a dependency on it. And once it computes itself, then the output can use that new data set to recompute itself, and we get our new graph. All right, so this is how event reactive works. You use event reactive to delay reactions. It creates a reactive expression, so you have to call the results as a function, just like with other reactive expressions. But you can specify precisely which reactive value should invalidate this expression. And usually you pair event reactive with an action button, but you could pair it with any sort of reactive value. All right. Go look at one last thing about reactivity in Shiny before we call it a day, and that's managing state. And this is a little bit about what I mean by that. We know that we have a list of reactive values in our app that we can work with. These are the input values. And those values will change based on user input. However, we can't change those values ourselves programmatically. You can imagine trying to set the slider to 25, and for your user, that would be a spooky experience. The slider moves back to 25. It might seem like your app was haunted or something. So as a general rule, Shiny doesn't give you the power to overwrite the input values in your app. But every once in a while, that sort of thing would be a useful thing to do. So what Shiny does give you is the power to create your own list of reactive values, which you can then overwrite as you see fit. Reactive values is a function that makes a list of reactive values. It's similar to the list function in that it doesn't take any arguments. I mean, it doesn't require any, but you could give it arguments to populate the list when you create it. So for example, this expression up here, it's going to create a reactive values list that begins with one element, named data, and that element will have inside of it 100 random normal values. I could add extra elements later after I create the list using the list syntax. I could write RV $data2 and save something in the data2 and so on. This is how I would use this in practice. Here's an app. It's the last script in your code folder, and it'll be easier to look at in RStudio. So we'll go here, opening 8reactivevalues.r. Let's run the code and then look at what it does. I'll stop the previous app, run this app. And what we see here is a simple app. It just displays a data set and a histogram. It begins with a normal data set, but if I click the uniform button, it displays some uniform data. If I click the normal button, it displays normal data. I could click the normal button again, it'll generate new normal data. And I can go back and forth. If we visualize this app in our slides, it looks like this. We have a reactive variables list that I created with one element named data. And downstream from that list is a histogram created with render plot. It takes a dependency on this reactive value $data object. When I click either of these buttons, it just overwrites the value of RV $data. If I click the norm button, that's the one that says normal, it overwrites that value with 100 random normal variables. When that happens, since RV $data is a reactive values object, it notifies the things that depend on it that it's changed. So now output hist knows that it's been invalidated, it reruns its code, looks up that value, creates the new plot. Something similar happens when I click input $unif. It overwrites RV $data with this time 100 uniform random values. That's a change, so output's notified, retrieves the new data, makes the new plot. And this is what I mean by managing state. We've created some persistent state here in RV $data, and now we're just programmatically manipulating that state through these action buttons. If we look at the code that does this, see that I created the reactive values object in the server function. That's where you should create them. I'm using observe event to run code that overwrites RV $data each time someone clicks one of those buttons. Now, one thing you'll notice about reactive values lists is that they share a syntax similar to environments in R, which basically means they're easier to look up from inside things like observe event. This code right here will find RV on the search path. I don't need to use a double arrow or anything like that. Shiny will take care of everything for me. Once I have this set up, my app will work as we described. All right, So reactive values, they create a list of reactive values for you to use, and you can manipulate these programmatically, usually with observe event and some sort of action button. All right. So what do you now know how to do? Quite a bit. You can render reactive output with render. You can modularize your reactive chains with reactive. You could isolate values so they stop the reactive chain with isolate. You could trigger arbitrary code with observe event or observe. You could delay reactions with event reactive. And you can even create your own reactive values to use at the start of your reactive chains with reactive values. So this is probably the most technical of the 3 webinars, and I thank you for paying attention this long. You can see that you've learned quite a bit about customizing your Shiny apps along the way. Before we stop, I want to leave you with 2 parting tips. And the first is to keep in mind what the end result of your Shiny application is going to be. If you are going to host this application online, for example, a Shiny Server Pro, it's going to end up having an architecture similar to this. You write one single application, it gets hosted on a server. In the world of virtual computing in the cloud, that means that there will likely be multiple instances of this application existing as more and more people visit your app. Amazon will fire up instances to handle those people. You can ignore all that. But as people come to visit your app, each server instance will open up new R sessions to handle those people. A single R session can handle multiple people using your app, but you can imagine somewhere along the way when 100 people are trying to use the same R session, your app might start to slow down. So the server is designed to open up a second R session when needed, or a third R session to handle additional people as they show up. And then each person, when they get to the app, they have their own fresh copy of the app, and they experience their app and no one else's app. It's all very secure. But this hierarchy of R sessions and users affects how you should write the code in your Shiny app. Depending on where you place your code, it will be repeated multiple times. If you write code and you place it outside of the server function, it will be run just once each time a new R session is created. So think of your computer. When you write a Shiny app on your computer is the server. Your R session is the session that's serving that app. You can define the UI object just one time, the whole time you have your computer on. You could call library Shiny just once the whole time you have your computer on. Those things will persist throughout the life of that R session until you close R. In fact, we could run everything but the last line of this Shiny template here just one time, and they'll stay in our memory. And then every time we call Shiny app UI equals UI server equals server, we'll use those things we defined just once. We might use them multiple times if we call that function multiple times. If you only need to run your code once to set up the R session, for example, to load a help file or load a library, place that code outside of the server function. Code that appears inside the server function will be run once per user who logs into your R session. Now that's a little harder to imagine when you're working locally, but if every time you fire up an app on your R session, that's like a user appearing and using your app. When you close the app and fire it up a second time, that's like a second user appearing. And you can see already that there will be more users than R sessions involved with your app. So code that appears inside the server function will be run more often than code that appears outside of it, which means it'll take up more resources and your app will be slightly slower because it's doing more things. So if you don't need to run the code once each time for each user, put it outside of the server function. If you need to run that piece of code once for each user, put it inside the server function. And then finally, you'll be making outputs using render functions to make them. And the code inside of a render function gets run most often of all. Every time someone switches an input, that code will be rerun. It might be rerun 100 times a minute or so. So you should put the bare minimum code inside a render function that is necessary for updating that rendered output. So that's the first tip I have. Think about where you call the code in your Shiny app. And then the second tip is more abstract. If you're like me, I knew R pretty well before I started using Shiny, and it was a real stumbling block to me to imagine how Shiny was actually creating this reactivity, because based on what I thought I knew about R, I just thought, well, there's no way R can behave like Excel. That's not how R works. Well, you could search through the source code for Shiny and figure out and satisfy yourself that yes, it does work. the source code is pretty complicated. So I've written an article that explains it in easier to understand terms. This won't necessarily help you write better Shiny apps unless this is something that's been distracting you and making you wonder. So feel free to ignore this. It's just if you feel inquisitive. And then finally, if you want to learn anything about Shiny in the meantime, I encourage you to go to the Shiny Development Center at shiny.rstudio.com, where we have a gallery of example apps, a tutorial that you can take, and articles that cover deeper topics about Shiny. So thank you very much for your patience. I know this webinar ran slightly longer than last time, and I know it's definitely much more technical, but I think it is also more empowering. The things you can do with Shiny now are pretty impressive. You just need to assemble them in creative and sophisticated ways.